This video is going to cover the Rescorla Wagner model of classical conditioning, and if you are watching this video, I'm going to assume that something like this happened to you. So maybe this is you. You're hanging around in your psychology class, you're having a good time, you're learning about the brain, and then out of nowhere, math. And I know the whole reason why you're a psychology major is because you weren't planning on having math in the first place, and so now you see something that looks like this. This is math. This doesn't even have any numbers in it.
No, God! No, God, please, no! 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 No!
So let's take a look at the outline for this video. We're going to be covering what the Rescorla Wagner model of classical conditioning is. We're going to be looking at a laboratory example using lab rats, and then we're going to look at a more applied example using something you might expect in the real world, and then we'll cap it off by talking about why this model is important, why it's being taught to you, and why you should know about it. So let's take a step back and let's look at the equation. Oh, there it is in all of its scary glory. Let's focus right now on this outcome variable, this thing at the end, the delta VA. What that is going to be a measurement of how much you have learned about a certain stimulus. We can call it stimulus A, but it can be whatever you want it to be. So we're looking at how much has changed with a new trial. So that's delta VA. Let's look at another parameter. Let's look at this next one, this alpha A right here. What this is going to be the saliency of stimulus A. So we're going to be basically looking at the associative value of whatever conditioned stimulus we're talking about in this example. Next we have beta R, and beta R is going to be kind of like an intensity value. So it's an intensity value of the unconditioned stimulus or of the reinforcer. If you want to apply this to operant conditioning, that's fine. And then this thing that we have down here in the parentheses, that's going to be the upper limit of the associative value of the unconditioned stimulus. So basically, how much can you possibly learn from it? Because not every stimulus is created equal, as you already. And we will learn to calculate these in just a moment. But first, I want to tell you about the secret to the Rescorla Wagner model, which is that learning is all about surprise. In other words, when we learn something, we're surprised by it. But if what happens is exactly what we expect, then we don't necessarily learn as much. So we need that surprise in order to learn stuff. So let's take a quick look at a basic conditioning example involving a simple lab rat. And this is going to be a fear conditioning study. It's going to be very simple, very straightforward. And the question is, what predicts a mild electric shock? Is it a buzzing sound or is it a red light? So we have these two neutral stimuli that we're going to see whether or not they are conditioned stimuli for this element of fear. So we're going to focus on this light right here and this speaker right here. So keep an eye on those things, and we're going to see which of these two stimuli is going to predict an electric shock for this rat. I'm going to call this rat, I'm going to call him Maestro. So right now, we don't know what to expect. And so we're going to say that the V1 for the light and the V2 for the speaker are both set to 0. We don't expect any kind of learning from them. Now we have the red light going off, and oh, Maestro has been shocked. So Maestro is surprised, right? Maestro is surprised, and because he's learned now that the red light is equal to shock. So we're going to move this stimulus value up to a V1. In other words, the prediction was no pain, but the outcome was pain, so we have error in the model, and we need to recalculate V1 to be 1. The red light goes off one more time, and he gets shocked again. Now, Maestro is not really all that surprised because he's already learned that the red light means that he's going to be shocked. So V1 is still going to be 1, and V2 is going to be 0. So the prediction was pain, the outcome was pain. There's no error in our model. But let's change it up a little bit. Let's say that this third trial, the speaker comes on, but the light doesn't. In this case, Maestro is just wondering, hey, who cares, right? Because it doesn't look like the tone is going to predict the shock, and so he hasn't really learned anything. These values are going to be unchanged. So when we look at our model, we predicted no pain, and the outcome was no pain, which is great. Let's look at the fourth trial here. So in this fourth trial, he gets shocked without any kind of warning. And so he's thinking, this is weird because I feel like I should have seen that light if I was going to get shocked. So we're going to readjust this value a little bit. And now it's time for us to recalculate the associative value of that red light. Now it's at 0.75 instead of just 1.0. Now let's say that the red light and the speaker both come on, and hey, Maestro gets shocked again. Now Maestro is going to learn a little bit here. He's going to learn that the light is a little bit more predictive of that shock, but he's not going to learn anything about that speaker, and this is called blocking, which is a fancy way of saying that basically Maestro has not learned that the speaker has any predictive value of whether or not he's going to be in pain. Okay, so let's look at a real world example, and I want you to consider your least favorite professor, and they are your least favorite professor because they keep assigning you pop quizzes. The question though is, can you predict when a quiz is coming? So let's lay it all out here. First, we have our possible predictors. Maybe he frowns when he enters the class, he doesn't have coffee, or he's carrying a bag of papers. The outcome is going to be, is there a quiz? And now we have kind of this setup where we're going to be looking at the error involved based on our prediction and the actual outcome. Okay, so let's look at the first day of class. So on the first day, we notice that he's frowning when he enters the class. So the question is, what do we expect? Well, we don't have any prior experience, so we're going to say no quiz, which means that this stimulus value is going to be 0, and the outcome actually is no quiz. And so if we're looking at how this impacts our model, our prediction was no quiz, and our outcome was no quiz, which basically means that the stimulus value, V1, can stay at 0. So let's take a look at the second day now. You notice that he doesn't have any coffee. So what do you expect? You don't really expect anything because you have no prior experience with this. So V2 is going to be 0, but oh god, he had a quiz. Crap. So this means that we have error in the model because our prediction was different from the actual outcome. What we predicted was no quiz. Our outcome was that we did get a quiz, which means that we need to recalculate V2 to be 1.0. To the third day, we have frowning when he enters the class. He doesn't have coffee. So what do we expect here? We expect that there's going to be a quiz because of this V2 is equal to 1. And so the outcome is, yes, there is a quiz. So there is no error in our model because we predicted a quiz and the outcome was a quiz, which means that V1 and V2 are going to stay exactly the same. Now let's fast forward to day 4. And on this day, all 3 possible predictors are here. What do we expect? We do expect a quiz because he doesn't have coffee, and yes, we're right, so there's no error in our model. We predicted a quiz, the outcome was there was a quiz, but what if the real reason we had a quiz was because he was carrying a stack of papers? Well, this leads us back into blocking, which means that we don't actually learn that carrying that stack of papers actually matters. So looking at the 5th day, we can see that he's frowning when he enters the class. He doesn't have coffee, so we expect there to be a quiz, but oh, there's no quiz, which means that we do have error in this model and we need to recalibrate V2. So our prediction was a quiz and outcome was no quiz, which means that we have error in our model and we need to recalculate the stimulus value for that. So let's get back to basics and let's look at how the Rescorla Wagner model actually focuses in on this V2, on the fact that there is coffee involved. So let's apply this example to this equation, and we can see how this works. So let's focus on alpha 2 here. So we're looking at how salient is the presence of coffee involved here. So how noticeable is it? Now let's look at the result variable, so delta V2. Basically, we're looking at how predictive is the coffee. Does it change? Is it more predictive or less predictive as a result of that particular day? Beta R is going to be the intensity of the quiz, because in this case, we're kind of treating the quiz as like an unconditioned stimulus because it makes us feel unpleasant. And then this parenthetical statement is going to be the top limit on how predictive that quiz can possibly be under the best circumstances. But if you're still upset that you have to learn about this, you can blame these two guys, Robert Rescorla and Alan Wagner. This comes out of their work from the 70s, and this was a super popular model at the time, and it still is because it is very reliable and is very predictive of different kinds of behavior, especially associative learning. And because it predicts blocking, which at the time was a huge problem for learning scientists trying to find a way to accurately predict when blocking was going to occur. But this isn't the end of the story. People are still using the Rescorla Wagner model, and it looks like it even has a neural basis in our dopamine pathways. These pathways, which are located in the middle of the brain, in the midbrain, seem to calibrate themselves based on the same error prediction that we just went through at trying to learn how predictive certain outcomes are. But the Rescorla Wagner model isn't perfect. It does have a couple limitations, and they have been kind of revised in the subsequent years. One of these is that it doesn't really account for latent inhibition, which is whenever previous experience with stimuli kind of inhibits your ability to learn or to learn to predict certain outcomes. It doesn't really account for spontaneous recovery, which is whenever a conditioned response seems to come back after extinction. It doesn't really account for reacquisition or savings that you get from learning. So, for example, if you have learned something and then you quote-unquote forgot it, you might be faster at picking up or learning that association the second time around. And it doesn't really account for sensory preconditioning, which is whenever you learn things that are paired before any kind of conditioning takes place, and this model doesn't really account for that. Alright, so that's it. That's the basic overview of the Rescorla Wagner model of classical conditioning. This nasty equation right here, just keep in mind that it is all about surprise, that surprise equals learning. So if this video was not helpful for you, then we would say that delta VA is equal to 0. Alright, that's all that we have time for. Bye.